Okay, so yeah, so what I'd like to do in a sort of terse way is tell you about the version of the Appell-Humbert theorem for holomorphic gerbes. So I found that some guy had written a paper on
Was
that.
this that guy Ben-Bassat or something?
Yeah,
like that?
Ben-Bassat.
Yeah, that was interesting.
In 2008, I think. And it took me a while to understand it, but the result winds up phrased in a certain way. It winds up looking a whole lot like the Appell-Humbert theorem for line bundles, and it also, phrased in a certain way, has a really plausible generalization to n gerbes, because you can sort of maybe guess what from this way how it's going to keep going. So let me share my screen and write some stuff. So let me state the Appell-Humbert theorem for line bundles in this way that is designed to make it look as similar as possible. So it all works when X is a complex torus, even though one is most interested in the case of a abelian variety. One interesting difference between the line bundle case and the gerbe case is that, of course, for a complex torus to be an abelian variety is the same as having a polarization, which is a special kind of line bundle. But Ben-Bassat points out that you can have interesting gerbes in cases even when they're like really few or like non-trivial line bundles.
That's interesting.
So the gerbe case, at least to some extent, seems to like chew away the dominance of abelian varieties. So, okay, so the class one, well, so classically you have this kind of thing for maybe like more generally than for complex tori. Well, definitely more generally than complex tori, maybe like at least for varieties or maybe for like some kind of complex manifolds. So the idea is that, as you know, so this guy is the group of isomorphism classes of holomorphic line bundles. And then this guy, you could say, is like the group of isomorphism classes of topological line bundles or smooth line bundles that come from, that admit a holomorphic structure.
Yes.
And then for any complex line bundle that admits a holomorphic structure, so it's in the image of this, then there will be potentially lots of complex, lots of holomorphic structures, and they will form this group or form a torsor of this group, I guess, in general. And so this guy here, you might as well just say is like the group of isomorphism classes of holomorphic structures on the trivial line bundle, if you want to be sort of specific about it. And so then so that's a sort of general thing. And then when you have a complex torus, Appell-Humbert kicks in. And so I think that your way, not your way, the way that you impressed upon me of thinking about this is going to be the easy way. The other way is also nice, but the easy way is to say that this is like the 1-1, the cohomology, and I'll just write like intersected with the integer cohomology. Although I like to remind myself that there's like really a map from the integral cohomology to the cohomology with complex coefficients.
Yes.
There can be torsion in here that gets
Okay. Yes.
that will get killed. So this is not like a subset. This is not this is not like a subset of the complex subgroup of the complex cohomology, but it maps to it.
Yeah, I think my excuse for not worrying about that yet is just because I really have been thinking about the case of X being a complex torus, and I don't have to worry about that for complex torus. Is that right?
Oh yeah, right. Yeah, that's true. Yeah. So okay, so then this is like even right. Yeah, so actually, I mean, this part here wasn't Appell-Humbert. Yeah, this is still works like probably for like any compact, complex manifold, and certainly for any algebraic, projective algebraic variety over the complex numbers.
Really mostly just thought about it for the Abelian varieties and complex toruses, but yeah, I guess it could be.
Yeah.
For very general.
I think this stuff, I mean, yeah, this stuff certainly works for complex
projective
varieties, but because I sort of went out to torus, it sort of makes me want to go to complex manifolds of some sort for this stuff, but I don't really know that. I bet
right.
it's true.
Right.
So I don't. And then this one, the way to think about this one. Now I'm really using the fact that we've got a complex torus. Is well, like one way to think about this one is that it's this dual torus. And there are different ways to think about what the dual torus is, and to make this all generalize the most pleasantly, a way that's nice, which is like different than the ways that I was talking about. Well, no, I mentioned it before, but it was like different than my favorite way, but it's nice. So you think of your complex torus as a vector space mod a lattice, and then you look at the abelian group homomorphisms from the lattice to the circle, or U1 or whatever you want to call it. So this is
yes
that's Pontryagin dual for the lattice.
Yes.
And it gives you a torus. So this is all like lined up in a way that's like designed to, hopefully if I don't screw up, it'll lead smoothly into Ben-Bassat's version for holomorphic gerbes.
Okay.
Yeah. So let me tell you the version for holomorphic gerbes. Maybe just like to stall for time or something. I'll say like this. There are these other descriptions of the Néron severity group in terms of the Rosati involution or other things.
Yes.
And those, well, some of those also work for the gerbes, but they're sort of a little. The one that Ben-Bassat talks about is a little surprisingly different for gerbes than in the traditional line bundle case. So I'm not going to talk about that one because that would just like make it seem weird. Whereas I'm trying to make it all seem like straightforward, or smooth or something. Okay, so next one. So this is like, that was for line bundles. So now for gerbes. So the same. So like the same setup. X is a complex torus. So there's this thing, which I'm just going to call peak 2 of X. And so what this is sort of the thing that's like Picard group. So it's the group of all equivalent classes of holomorphic gerbes. So there's a two category of holomorphic gerbes over X. So instead of isomorphism, we should work with equivalence in the two categorical sense. And we can tensor gerbes, and so the set of equivalence classes forms a group.
Okay.
So, I mean, there are other things you could try to make a two group or something out of it, but we're just going to make a group. Okay, and so then any gerb, sorry, these are holomorphic equivalence classes of holomorphic gerbes. Any holomorphic gerb has an underlying topological or smooth gerb. And so you can do the same kind of thing we did before, define a kind of Néron-Severi group.
Does Ben-Bassat call it anything like that? Or?
No, he has some fancy, interesting other name for it that involves, I forget now, sorry. A very different name for it.
Okay.
But definitely it's what this is. So what this thing is the group of equivalence classes of, let's say, smooth gerbes, which probably, or topological gerbes that admit a holomorphic structure.
Okay.
And now smooth or topological gerbes are classified by the third integral cohomology.
Yes.
Just like before they were classified with the second integral cohomology.
Right.
So this should be some sub thing of the third integral cohomology.
Right.
But let me actually say exactly what it is, because Ben-Bassat says exactly what it is, and it's very interesting. So to build up the suspense slightly, so it'll be like the intersection of the third integral cohomology.
Yes.
With something. And I think I mentioned this in email, like if you try to follow your nose, you might do like H to the 3/2, comma 3/2 here, like going straight up the Hodge diamond. And that's
right. That was my original idea. Right.
Yeah. Oh, okay. So no, but but it's sort of oddly, and I do not understand this at all. I don't claim to understand this at all. It's sort of the next best thing, which is it's intersect the direct sum of the 1, 2 and the 2, 1.
So it really is just this intersection.
It really is just this intersection. Yeah. So there's a more complicated description of this thing that is analogous to the description of the Néron-Severi group in terms of alternating bilinear forms that have some property that says they get along with the complex structure.
Right.
But that, while it's not incredibly complicated, it's maybe a little more surprising than this was. And I think that if I really understood what was going on, I could like work out that style of description from this style of description. That is, the cohomology, the third cohomology of X is just like anti-symmetric trilinear forms on the lattice L, or on the vector space V, I guess, if we're doing like real coefficients. And so you should be able to like describe the Hodge structure on that, and then like pick out the different parts in a kind of a formula style way in terms of like what properties those anti-symmetric trilinear forms should have. And it should, so this should like, this description should translate into like a more sort of more grungy, but also sort of more computationally friendly description. Because, this one, it's like, it's sort of hard to know how you're going to figure this out. So, but anyway, this has the advantage of being sort of easy to remember, although still sort of mysterious. I really do not know how it manages to split the difference like this. Okay, but marching right on. So then there's this thing that's like the Jacobian, which I'll call Jac2 of x.
Yes.
So what this is.
So people really do call that.
This notation is all mine. All mine. No, he doesn't. He doesn't say any of these.
Well, actually, right. But I was just asking. Actually, Jacob back in the one case, they do call that the Jacobian. They also call it the Picard variety.
They call it the Picard variety. And
if you're thinking of it as a variety.
Yeah, I've sort of been shunning that term when I realized that I'm working with complex tori a bunch, where it's not even a variety. I guess you could call it the Picard torus or something.
Right. Okay.
But it is also the Jacobian.
Okay.
So, and calling it the Jacobian is like a good thing because like this first part here would like work for any variety. Yeah, it would work for. I think there's a thing. I think this idea, the way I've defined these three things, it works for any projective algebraic variety, and so then they call this thing the Jacobian. So. Well, they call it the Picard variety. Why am I saying that? I don't know. Yeah, they call them both things.
Okay. But now we're back to 2. Okay.
Yeah, so back to 2. So what this is it's the group of, well, you can sort of say slightly more concretely, it's the group of equivalence classes of holomorphic structures on the trivial gerbe.
Yes.
But then because of this exact sequence, any gerbe that has a holomorphic structure will have Jac2 of x's worth of them. So
yes.
Yeah. So okay. And then this one, Ben-Bassat describes very beautifully. So before it was this dual torus. So now, if I have it,
yes,
if I have it right, let's see. I think what it is. Let's see. I think what it is it's just of. So you can take like this lambda 2 of your lattice. Lambda 2 of your lattice, yeah.
Yes.
And then that's some new lattice sitting in lambda 2 of the vector space that it's in.
Yes.
And then you go from that into U1.
That certainly is suggestive of a pattern. And again, it's a funny pattern, but over on the discrete side, we have the one higher index.
Yeah, that is funny.
Side.
I think that has a whole lot to do with like long exact sequences and sheaf cohomology that where you like get this kind of jump going up from like some first cohomology up to some second as you march along.
Yeah, I mean, I'll have to think about it, but it's a very suggestive pattern.
Yeah, we had a lot of nice things to say about this original case, and I think we weren't quite done. Done thinking about that case, but this. So
yes. But can you go back to the one case just for a second? The screen. I forgot to ask. When you write it as the Pontryagin dual like that, is there anything that's manifestly making it into a complex manifold?
It's hard to see that it's hard to instantly see it from this description. You're right. And so.
But it is somehow. It's very easy to believe that there is somewhat.
Yeah. Well, so the other way to describe it is like better for that purpose, which is that you say that it's, and I think I can do this. So you can say that this turns out to be sorry, I'm going to the Derby case. Sorry, I can think of it like this. It's like the dual vector space, which is a complex vector space, over the dual lattice. And then since this is a complex vector space, then this is a complex torus.
Okay, that's good enough for now.
Yeah. And well, but since you mentioned it,
yes.
So actually Ben-Bassat doesn't say this. So I think what he says actually is this, which is lambda 2 of L dual. Sorry, backwards. Sorry, he says this analogous thing for the Derby case. Sorry. Lambda 2 of the dual vector space mod lambda 2 of the dual lattice. So there's this dual vector space and it contains this dual lattice. And you can take the second exterior power of this dual vector space and it will have this lattice in it that's the second exterior power of the dual lattice. Remember what's going on here.
Okay, but the first thing you wrote there, you could just describe that as the Pontryagin dual of this exterior square of the lattice or something?
Yeah, that's right. But then, and I'm actually just guessing that this is the same as this. What Ben-Bassat says is the second description. But I think I almost know this, that this kind of thing is like a general thing that like there are two ways to describe. I mean, here it was sort of the general case. There are two ways to describe the dual of a torus, which are these. You take the dual vector space, mod the dual lattice, or you ham the lattice or you take the Pontryagin dual of the lattice. This confused the hell out of me for a while because it takes a little bit of thought to see why these are the same. But
it's very plausible.
It's mainly plausible because it's like the only ways I can think of getting a dualish torus out of. Yeah. But yeah, I mean, it's a known thing. Yeah. So basically, what we're doing on the second page here is we're applying that two descriptions to the case where we've got this second exterior power lattice sitting inside the second exterior power vector space. So this is like a lattice in that. So this will have, so the dual of that will be either of these two guys. The dual of the torus.
I don't want to worry about this too much yet, but when I go home, I should really think about, I mean, don't I have to be careful about exterior square of a real vector space versus of a complex vector space or something like that?
Yeah, you definitely do. Yes. Yeah. Okay. No. Yeah. You're right. Let's see.
But again, I can worry about that when I go home or something.
Yeah. So right here, I probably do mean I definitely mean the real vector space. V star is being treated as a real vector space when I'm taking its exterior square. So you have to, okay, yeah. So it's not so, yeah, you're right. So it's not so obvious to me how this gets to be a complex torus. But one of the things, there's probably ways to make it more obvious, but one of the things is that these kind of higher Jacobians, they're called intermediate Jacobians in the.
Oh, I have heard of those.
More classical literature.
Yeah, I have heard about that. I forgot about that. Intermediate Jacobians. I wasn't expecting them to show up here, I don't think, but I have heard of them.
Yeah, so on the NLab, there's a page written by Urs Schreiber, who at some point or other was telling people like, oh my God, intermediate Jacobians are just about gerbes, higher gerbes. But the reason why I mentioned it right now is that Dolan had described complex structures on all the intermediate Jacobians.
Right.
So there's like a description of them that's basically just this, that like, or this is like the real exterior powers. That doesn't instantly make it obvious why it's a complex torus, but it is. Then a guy named Griffiths, well, the algebraic geometer Griffiths, came up with like a different complex structure on the intermediate Jacobians.
I vaguely heard of that too, yes.
Yeah, but just out of wild guessing, I'm guessing that Dolan's one is the one that we want here. But anyway, so the point is that this is like something that getting this complex structure that you're wondering about is like something that people were worrying about. Succeeded in getting.
Yes.
So anyway, yeah, so this is really great. And hopefully it keeps on going like that, and with like some funny kind of switch back and forth between the even and the odd cases as to whether you have to do this trick here or not.
Oh, that's what you think it is?
That's what, oh, okay.
I was going to ask. Well, yeah.
Well, I have no idea. That's just my guess. Yeah, I guess it's just like continue the sequence.
I thought it might be the other pattern, that, it just keeps on getting wider and wider.
Okay, well, okay. Yeah, I have no idea. Okay, you're right. You're right. I don't know. It's just like if someone tells you what comes after these numbers, 2, 4.
Yes.
Someone will say, oh, obviously 6, and the other person will say, oh, obviously 8.
Yes.
But I hadn't even thought about the other possibility. So I don't know. I don't know. I think, yeah. So anyway, well, I think it means that I need to like actually understand this stuff a little bit better to. So like somehow or other, this condition here is like the condition that you're, well, if you think about it in terms of like multilinear forms on the lattice, this is like the condition that they get along with multiplication by I on the vector space.
Something like that, yeah.
But anyway, so like I said, I should be able to like work out that condition from this or work out this from that condition, but I haven't yet. So anyway, this is all I had to say.
Yeah, that's good. That's good. So again, I'm hoping, yeah, this looks nice and simple. So it's about as simple as I was hoping, I think. I'm hoping that one of the stories that, makes this more conceptual is, I mentioned this in email, it's just continuing this idea of descent from the universal cover of the complex torus. That's my vague idea. I haven't worked anything out about that yet, but except back in the case of the line bundles where,
Yeah.
I mean, so that story has a lot to do with, like factors of automorphy factors and stuff like that. So I wonder to what extent it's good to categorify that intuition about, automorphy factors and theta functions. I don't know, but
yeah, that could be really interesting. I think I have vague memories of someone trying to generalize theta functions to gerbes, but I may be imagining it. It could be that yeah, so I don't know. I mean, yeah, just obviously like a line bundle will have these sections, which will be your theta functions. A gerbe has sections that aren't section-like things that aren't functions. So the functions would come in at some other point. Maybe the sections would contain, the sections could have sections, which would be functions or something like that.
Yeah, I really haven't thought about this yet, but something like this seems worth thinking about.
Yeah, I bet there should be a lot of great stuff here, and I don't really have enough of a sense of how much people have thought about it. They may have like thought about it not so much from the gerb, not using the gerb language, but to some other language. So the one buzzword that's really relevant here is Dolan cohomology. So
I don't really know what that is.
This Dolan cohomology.
I guess I have heard it, but I don't really have any idea what it is.
I guess like the good, well, this may not be good for you, but this may be good for me.
Yeah.
So these days people have realized that Dolan cohomology is interesting in physics because, like, at one point people thought the electromagnetic field was, well, they thought lots of things about it, but at one point they thought it was like a vector potential, which is like a one form.
Yeah.
And then at some more sophisticated level, they thought of it as a connection on a trivial line bundle. That's basically the same thing as a one form. But then like a more sophisticated point of view is to think of it as like a connection on a line bundle. It may not be a trivial line bundle. So like in the Bohm-Aharonov effect or something like that, you think of it as a one connection on a non-trivial line bundle.
Yes.
And so string theorists and other highbrow theoretical physicists now try to think of the electromagnetic field as the combination of the line bundle and the connection on it. And that combination is like a key kind of thing you think about in Dolan cohomology.
Okay.
And so somehow that's like a combination of a one form thing, a one formy thing, like the connection. It's locally like a one form, and this sort of more two formy thing, which is the curvature of the connection.
Yes.
It has to be like an integral two form for you to get a line bundle associated to it.
Yes.
So that combination of like an integral second cohomology class together with a connection on the line bundle that it's describing, that's like some kind of Dolan cocycle. And so that's very
semi-plausible.
That's supposed to be sort of vaguely similar to what's going on here. That like
sure.
Yeah, it's got like this discrete part that involves cohomology at one level, and this continuous part that involves involves stuff at the one lower level.
Sure.
Actually, it's even more like this one, of course. So like in H2, this is like enough to describe a line bundle, and this is enough.
Yes.
Normal. The kind of Dolan cohomology that I'd heard about in physics was not dealing with a holomorphic case. It also is a thing that exists in the smooth case, but this is like a holomorphic Dolan cohomology business.
Well, that's okay. I'll have to think about that, because in this context, it sort of seems like the holomorphicness that's producing this mixture. But I'll have to think about that.
Yeah, it is. But then, yeah, so I don't completely understand it, but you could also say like, I'm going to take a guy in H2 of X, which is picks out just a topological line bundle or a smooth line bundle, and then I'll pick out like a connection on that bundle, which that's a lot more choice than this thing. That's not just like living in a torus. That's still a lot of data, but there's some analogy going on here.
Okay.
It's like there's smooth Dolan cohomology and holomorphic Dolan cohomology. So I have a feeling that like Dolan went ahead and thought about this stuff a bunch.
Yeah.
And that part of what he came up with while doing that was these complex structures on these intermediate Jacobians.
Okay.
And so it could be that like he went a lot further than that, and that I just don't know yet. And that he did all this like not using the language or anything, but it could be that it secretly was about gerbes and n-gerbes from in modern, if you think about it in a modern way. So anyway, maybe I can try to find out what he was up to. He was probably up to, something big. He was probably up to something big. This is probably just like the beginning of whatever he was doing. So like maybe he was categorifying the theory of theta functions or something like that without saying it that way. I have no idea. Okie doke.
Okay.
I'll just quit that.
Okay. Okay. All right. Let's see. Maybe I can just try to. Is it? Just in case I use this whiteboard thing here. How do I grab the
oh, do I have to let you
share screen? What?
Oh, I do. Yeah, I should be able to do it. If you see that green thing that says share screen. Yep.
What's showing up on your screen? Is there a
a whiteboardy thing?
Yeah, whiteboardy thing, right. Not sure I'm gonna really use it much, but let's see. So all right, so I'm going to try to explain. Let's see. I'm going to try to explain the belief method. So I also sometimes call this the categorified Grosvenor basis method. But you shouldn't take that too literally. It might be actually interesting to actually more literally categorify the Grosvenor basis method. That's not what I'm doing here. So this is somewhat of a. So why do I call this the categorified Grosvenor basis method? So what does it's because the goal of the belief method is to do something similar to the goal of the Grosvenor basis method, I think. And so the Grosvenor basis, the way Grosvenor bases are used, the way they're applied, is well, they're a very powerful technique, and I mean, maybe it's true of every powerful technique in mathematics that when you use it, you feel like you're cheating. You feel like you're getting something for nothing, something for free, and this is supposed to be kind of like that. So what am I trying to say? It's like well, when I say cheat, it's also like you're doing something illegal or something. So the illegal thing that some people like to do, for example, you and I always used to talk about how mathematical physicists always used to like to do this. It's sort of like sometimes described as gauge fixing, which is you're dealing with something that morally speaking is a quotient space, but you pretend it's a subspace. And that's called fixing a gauge or something like that. I'm not sure I remember how the terminology works, but you probably know better than I do. But so I mean, how is the Grosvenor basis method like this? Well, so Grosvenor bases can be used when you have like a presentation of a commutative algebra, for example, right? You have like a polynomial ring, and then you have an ideal generated by some polynomials. And you multiply that ideal, and you get a quotient algebra. And it's a quotient algebra. It's not a sub thing. But the Grosvenor basis method lets you think of the elements of the quotient algebra as some specific elements of the original polynomial algebra. So, right, it's kind of cheating. It's kind of
By the way,
you,
I've never really used the Grosvenor basis method, so I don't
me neither.
have a, well, I don't even have the guts to like act like I know anything about it. But okay, I have a pretty vague.
Yeah, it's not necessarily the
it.
case. It's not necessarily, you know, despite the little amount that you know, it's not necessarily less than I know. Again, it might be interesting to actually learn how this works, but I'm using it as a, you know, I'm using it as a story, really. I mean, you can also think of it as, right, so Grosvenor basis methods have something to do with like confluent rewriting systems, right? Where you have like presentations, and then you have like, you interpret the equations in a presentation as rewrite rules. But, you know, if you just let the rewrite rules act all haywire, then, you know, you can go around in circles. You can, but a confluent rewriting system is one where you somehow have it arranged so that you're not going around in circles so much. And you, after applying all the rewrite rules as much as possible, you end up with a final answer as to what's the best way to rewrite a particular expression. And in that way, it's, you know, so these dead end expressions that can't be rewritten in any better way, that's the sub thing. You know, these sort of equilibrium points under rewriting. That's the sub thing that acts as a substitute for this quotient thing that you want to understand.
Purely because I think someone may watch these videos sometime. I'll mention that that's confluent and terminating. So they're like two clauses in there to make you get to a dead end.
See that? So already you're showing that you know more about this than I do.
I wouldn't have said it, except that I'm imagining someone's like watching me, thinking like, he's just nodding.
Okay.
It doesn't really matter.
Okay. So, I mean, I think at some point I actually tried, you know, searching on the search term, something like Grosvenor gauge or something like that. And I don't remember whether I found anybody, you know, I may have found my own old ideas, but I'm not sure I found any. I think I did find somebody else thinking along those lines, but I don't really remember. But well, before I start giving the definitions of what a belief doctrine is and what a belief is, before I start giving those definitions, let me say a little bit more about what the word believe in this context is supposed to mean. So the idea is, how do I say this? That, well, okay, so I call it the belief method, but the reason I called it the belief method is I claim that if you go back before I started calling this the belief method, and you read what mathematicians who are actually using this method, maybe without giving it a name or anything like that, but they used this name, they used this method in practice. I don't think they called it anything particular, but they used the method, and sometimes they would use the word belief. You know, so I didn't come up with the word belief, or at least I have found people who use it before I did, and use it in a very similar way. So I mean, at some point I should, I don't have the reference right handy, but there's a reference that I keep that, you know, actually it says, this guy is writing and he says something like, the objects that believe in fantasy that such and such form a Cartesian closed category or something like that. So the idea is we're going to create certain categories by taking the objects that believe certain things. So So, okay, so let me try to tell you the general context where we're going to try to solve some sort of problem here. So the general context is that we're going to have a theory of some kind, and we're trying to create the generic model of that theory. So, right, I mean, this really is, right, this is, I mean, like, right, if our theory is like a two-rig of some kind, then this is very much like, you know, trying to take, this is a categorified version of taking a presentation of a commutative ring. You know, think of a two-rig as a categorified version of a commutative ring. So we're going to have like a categorified version of a presentation of one of these categorified commutative rings, one of these two rigs. And we want to know what is the actual, right? We want to know concretely what the elements of this two rig are, rather than just knowing that it has a presentation. Right.
So when you say we're taking the theory and we're trying to create the generic model, I mean, the generic model, it is the theory, right?
That's right. That's right. That's right.
Okay. But you're trying to like figure out all the objects and all the morphisms.
Yes, we're trying to have it very concretely. You don't want to just.
Okay. Yeah.
So, so the story here about how the method works. Yeah. So there's another story here, and this story is it's called I guess it's called The Emperor's New Clothes or something like that, or it's some variation on The Emperor's New Clothes. So the idea is, right, the idea of The Emperor's New Clothes is, I don't know, I'm not sure what the idea is, but the idea is that there are these. Well, the emperor is an idiot, but his subjects are idiots too, I guess. But I don't know, somehow they believe, or they act like they believe something, and I guess the moral of the story is that they make idiots out of themselves. But I'm sort of changing the moral of the story. The moral of the story, the way I'm seeing it, is that they actually make the things that they believe become the truth.
Mm-hmm.
So it's actually a useful kind of delusion. And so, okay, so that's the spiel, that's the setup. But let me go ahead and try and give some definitions here, and let's see how we can try to get this to work. So let me start.
You're making me think of how
people
believe that money has value, and therefore it does.
Yeah, yeah.
That's useful delusion.
Yeah, something like that.
This piece of paper is worth 50 bucks. You can buy an apple with this thing. Okay, yeah. Uh-huh.
Yes. So, okay, so let me define what a belief doctrine is. Okay. So that's the context where we're going to be talking about beliefs and stuff like that. So, first of all, this definition isn't necessarily carved in stone. All of this should be thought of as usual. It should be thought as work in progress. We might change the definitions, might not have the best definitions, but nevertheless, I'm going to go ahead and give you a definition here of what a belief doctrine is. So, a belief doctrine is a monad on the bicategory of locally presentable categories. And I mean, this particular definition is not completely, unprecedented, not completely out of the blue, because, right, it does hark back to Lovier's use of the word doctrine as a kind of monad on a category of categories, or on a bicategory or something like that. So, so this is somehow following in that vein. But the definition is that a belief doctrine is just a monad on the bicategory of locally presentable categories. So of course you may you may be worrying about, well, how much am I supposed to remember about what locally presentable categories are, et cetera, et cetera. I'll try to say something about that. you know, we're not going to worry about it too much. We're going to try to convince ourselves that it has some very useful properties that's going to make a lot of things, doing a lot of things is going to become very easy because of the nice properties that locally presentable categories have. But so yeah, so let's see, we're going to have oh well, so again, there's this issue. I think when Lovier originally defined doctrines as monads, he had them being strict monads on the one category of categories. But I have a feeling that other people later decided, you know, as they started working with, you know, less strict kinds of things, that they had, you know, non-strict or strong monads on a bicategory or something like that. So this is, you know, this is very much probably more like that. So let me try to tell you what, let me try to tell you something about locally presentable categories, what's good about them. And yeah, one thing that's annoying about them to me is I don't like the name locally presentable categories. I'm not sure. I'm not sure. Not sure how it got that name, or to the extent that I am sure how it got that name, I don't like the name. So let me give you a couple of ideas about what locally presentable categories are. So one idea about locally presentable categories is that they form a nice adjoint functor theorem paradise. But if you're working in the bicategory of locally presentable categories, there are some very nice adjoint functor theorems that are easier to state than the adjoint functor theorems that you run into some other context. So roughly speaking, you know, adjoint functor theorems tend to say something like that a functor that has a left adjoint is roughly the same thing as a functor that preserves co-limits, except that there's an enormous amount of fine print in there. Like it says something about, I don't know what the fine print says these days. It used to say something about, you know, there's a solution set condition or something like that. But you know, there's a beautiful idea for a theorem. Then there's a beautiful idea for a theorem, but then it's marred by all this fine print. And so the idea of talking about locally presentable categories is that you can get into a situation where you don't really need a lot of fine print. So locally presentable categories are really just they're a version of categories that have colimits, but they're just designed for the colimits to behave in a very nice way, in such a way that these adjoint functor theorems will work very nicely. You know, basically the theorems that say that left adjoint functors are the same things as functors that preserve small colimits. Mm-hmm. So you know, there are other candidates for other slightly different adjoint functor theorem paradises, and it could be that maybe we should really adapt the belief methods to those things, like so there's total categories, and there are relatively nice adjoint functor theorems for total categories, but that's not what I'm going to do. For the moment, I'm going to stick with these locally presentable categories. And one way you can define what a locally presentable category is that it's a smallly sketched colimit theory. So, you know, it's a theory that the only syntax that is used in the theory is colimits. And the whole sketch of the theory should be small, you know, should just be everything in it should be a set. You know, you should be able to encode the whole sketch as a set. And so that's actually a reasonable definition. If you clean that up, that's a reasonable definition of what a locally presentable category is. It's really just a smallly sketched colimits theory.
For some weird reason, I thought I
heard
that it was a smallly sketched limits theory.
Those are the same.
Okay.
So-
Okay.
Because you
Okay,
can just,
that's why I,
yeah, you can just dualize. So for example, you could talk about the theory of groups or the theory of co-groups. So, as you know, a smallly sketched, the theory of groups is an example of a smallly sketched limits theory, but the theory of co-groups, did I say that right? Yeah, is an example of a smallly sketched co-limit theory. So it's just, some sort of abstract nonsense formal duality here. The reason I'm not,
are you switching from the textbook one or something?
I might be.
Okay, it doesn't matter too much, but I think I thought I'd like learn something about this stuff, and I thought they were like smallly sketched limits theory. So maybe you're.
Well, I mean, but the reason, let me give you the rough of, I mean, again, it's a lump in the rug, and you can sweep it around. It's still going to be there, but let me try to argue my side of it. Why I like the smallly sketched co-limits theories. It's because if I take, for example, if I take the theory of if I take if I take the theory of a co-group, that smallly sketched co-limits theory, then the syntactic category is the category of groups. Whereas if I take, the theory of a group, then that smallly sketched limits theory, the syntactic category of that theory is the opposite of the category of groups.
Yeah, actually, what I heard was that locally presentable categories are categories of models of a smallly sketched limits theory. Okay, but you're saying that's the same. Okay, so that is the same thing as what you're saying, that they are smallly sketched co-limits theories by this Appell-Humbert duality. I guess maybe you need that to like.
Yes, but I really want to think about these syntactic categories, not the model categories.
Okay.
Okay. Because to me, the theory is the syntactic category. And, so when I deal with something like, quasi-coherent sheaves over a projective variety or something like that, that's one of these co-limits theories. And, I don't want to have to talk about the opposite of that. So again, it's a lump in the carpet, but this is the way I'm going to try setting my convention.
Okay.
So, so that's what a belief doctrine is. So let's give a couple of examples of belief doctrines, okay? So I'm supposed to give examples of monads on this bicategory. I mean, supposing my job were to give examples of monads on the category of sets instead, for example, then, I could explicitly describe the monad, or I could just say, the monad for groups or something like that, right? I mean, there's the free group, right? Instead of explicitly describing the monad, I can just, sort of cheat or whatever and say what the algebras of the monad are. And so I'll do that. I'll do that here. So you could consider symmetric monoidal locally presentable categories. Those are the algebras of a monad on this bicategory. And and in this case, if you think about what the monad is like, it's not that hard to describe. It's something vaguely like a categorified. Don't tell me, is it categorified symmetric algebra? Is that the way to say it? I think that's right. Right. So I mean, these, very vaguely, these locally presentable categories, they're sort of like, categorified abelian groups or categorified vector spaces or something like that, right? Because co-limits is kind of like a categorified addition speaking very loosely. So, if you have a symmetric monoidal locally presentable category, it's sort of like a categorified version of a symmetric monoidal vector space or something like that. But that's a decategorified thing. It's just a commutative monoidal vector space. So that would be a commutative algebra or something like that. So this is a categorified version of that. So, so that's an example of a belief doctrine. That's actually a very important example of a belief doctrine. In fact, I mean, it could be that you could 90% of the time use that belief doctrine, and you could still do an enormous amount of interesting mathematics. But there's a lot of belief doctrines. I mean, for example, there's, instead of symmetric monoidal locally presentable categories, you could have braided monoidal locally presentable categories, or just plain monoidal locally presentable categories, or you could have Cartesian monoidal locally presentable categories, or you could have, well, so another very interesting one is Grothendieck toposes. And so actually between those two examples, that counts for an enormous amount of the subject. You could just study those two examples and you could get a lot of applications and a lot of interesting mathematics going. So the belief doctrine of Grothendieck toposes.
Does that one have geometric morphisms as the morphisms?
Yes. Again, you just have to straighten out which way the duality goes. So I mean, a geometric morphism consists of a left adjoint and a right adjoint. And then the left adjoint has some extra properties. Is that right? Yeah. But very often people pretend or claim to pretend that the thing they're calling the geometric morphism is the right adjoint or something like that. But I think it makes, and that's why they call it a geometric morphism, because they're sort of thinking geometrically, right? The right adjoint is going in the geometric direction, whereas it's the left adjoint that's going in the algebraic direction. So it's the left adjoint that's, more analogous to a categorified commutative ring homomorphism. So yeah, so one of the funny things that's going on here is you might notice that I have, these two very fundamental examples of a belief doctrine, and they're both in different ways. They're both examples, they're both categorified versions of commutative rings, but in peculiarly contrasting, but peculiarly related ways. Right, a symmetric monoidal locally presentable category, that's a certain kind of categorified commutative ring, so to speak. And a Grothendieck topos is also a certain kind of categorified commutative ring, but a slightly different kind. So let's see. So yeah, so I think I said it correctly when, if you describe the symmetric monoidal locally presentable categories, if you describe that as an explicit monad on the bicategory of locally presentable categories, I think if I didn't screw up, then I think I correctly said that it's a sort of categorified symmetric algebra. I think that's right. But on the other hand, if you try to explicitly describe the Grothendieck toposes as an explicit monad on this bicategory, I'm not really sure anybody's written that down, or maybe, very possibly somebody has written it down. But the last time Todd Trimble was asking me about this, I don't think we actually found out any place that this was written down. So what am I saying? That there's a forgetful functor, a forgetful bifunctor, or whatever you call it, forgetful two functor, from the bicategory of Grothendieck toposes to the bicategory of locally presentable categories. So right, the morphisms, I'm thinking of the morphisms between locally presentable categories as being the left adjoints, because those are the ones that preserve the colimits. And I'm thinking of these as colimit spheres. So Yes, so there's this forgetful functor from Grothendieck toposes, or forgetful two functor, or whatever it's called, from Grothendieck toposes to locally presentable categories. You just take the underlying category of a Grothendieck topos, and that's locally presentable. And the geometric morphism thought of in the algebraic direction, that is a left adjoint. So that, yeah, so there is a good forgetful functor there. And I'm claiming that that functor has a, that forgetful functor has a left adjoint, so that you get a monad out of this, and that the monads really are the Grothendieck toposes. So, yeah, so
is the part that's not spelled out so much anywhere as the left adjoint?
I think that's right, yeah. And again, it very well may be spelled out somewhere. I just, last time I thought about this, I don't remember coming up with any very explicit description yet. Or if I did come up with an explicit description, it just didn't seem very familiar. I didn't remember ever describing this, but somebody may have written it down. So, okay, so that's what a belief doctrine is, but I haven't given you much reason yet to see why that should be called a belief doctrine. But now I'll go ahead and try to give you some more idea of why that's called a belief doctrine. And I'll define what a belief is. So in what context are we going to define what a belief is? So let me think about this for a moment. So let's see. So suppose we have, well, so first of all, when you have one of these belief doctrines, then it's a monad, and that means that it has algebras, and those algebras form a bicategory. And this is a forgetful functor from that bicategory to the bicategory of locally presentable categories. And so these algebras for this monad, the algebras for this doctrine, they're called theories. And again, this is just following the way Lovier used the words doctrine and theory. The doctrine is really a monad. The algebras of that monad are called the theories. So again, we're following Lovier's ideas here to a great extent. It's also easy to imagine all sorts of things that would make Lovier unhappy about the way I'm doing this, but I'm not going to worry about that at the moment.
Yes. Sorry, I was talking about Lisa. No.
Right. But I should go ahead.
Yep.
Okay. So supposing we have so let's call our belief doctrine, let's call it D. Okay, let's fix one particular belief doctrine. Okay. And let's fix one particular interpretation of theories in this doctrine. So that means we have to fix two particular theories and one particular interpretation between them. So, so we have a D theory T1 and a D theory T2, and an interpretation J from T1 to T2. And, so if you think about how interpretations, morphisms of these theories are defined, so those interpretations, those should be left adjoints, but left adjoints, they're in addition to being left adjoints, they are algebra holomorphisms with respect to this doctrine. So for example, if the doctrine was the doctrine D of symmetric monoidal categories, symmetric monoidal locally presentable categories, then these interpretations of theories would be left adjoint symmetric monoidal functors, symmetric monoidal left adjoint functors. So in any case, we fixed a belief doctrine D, we fixed a D theory T1, we fixed another D theory T2, and we fixed an interpretation J from T1 to T2. And now let's fix some object in T1. So I'm going to call this C1, I think, for the moment. And the definition, I'm going to define what a J belief on C1 is.
Mm-hmm.
And there are going to be two equivalent definitions and a lemma stating that the two equivalent definitions are equivalent. It's supposed to be a very tautological lemma, but it really exploits the adjoint functor theorems that we have for locally presentable categories. So how does this work? So what is a J belief on C1? By the way, let me tell you what the letter, why, I chose the letter D for doctrine. I chose the letter T for theory. You don't have any idea what I chose the letter C for? Should I tell you?
Nope, nor J for that matter, but yeah.
Well, J to me is just another version of I. That's for interpretation.
Okay.
And C is for construction. So I have a feeling other people don't really use that terminology, but to me, the objects of a syntactic category are constructions, things that you construct from, the basic stuff in the theory.
Okay.
Okay. So, a J belief on C1. Let's see if I can remember what it is now. I guess part of the difficulty is trying to remember which of the two equivalent definitions I'm doing at any given moment, because if I get them mixed up, I'll get them backwards. So let's see. Okay, I'll take a stab at it, and then if I make a mistake, we may have to fix it, but I'll take a stab at it. So it is a J belief on C1 is a strong lift of C1 along the right adjoint of J. So what do I mean by a strong lift? It's an object C2 in T2 equipped with an isomorphism between the right adjoint of J evaluated at C2 and C1. So I'm calling that a strong lift. I guess a strict lift would be if it were equal, but having the explicit isomorphism makes it a strong lift. So that's one of the equivalent definitions of what a J belief is on C1. But the alternative definition is that instead of being a lift, it's an extension. This is something that's supposed to be, by the adjoint functor theorems, it's supposed to be equivalent to that lift. So it's supposed to be something like this. It's supposed to be, how do I say this? We take the Hom functor of C1. So what do I mean by the Hom functor of C1? So, is it the covariant Hom functor or the contravariant functor or what? It should be if I'm not getting it backwards, it should be the functor humming into C1. So that should be a functor from T1 up into set. Is that right?
Yeah.
Okay. Now, at the moment, I'm assuming that we're working over the category sets here. Everything is over the category sets here. But we really should be prepared at some point to really relativize this. We may be working over other categories besides set. Especially we may be working over complex vector spaces or something like that. But so be prepared for that. But for the moment, I think I could stick with this set value thing. So we've got this contravariant set valued functor, which is humming into C1. And that goes from where? That goes from, I already said where it goes from.
T1 up to set, yeah.
T1 up to set, okay. So
you want to extend it to T2 op?
Yes, exactly. Exactly. In a left in a co-limit preserving way. No, did I say that right? I think it's going to end up being in a limit preserving way. Well, let's see. I have to think about that. The op here is making it confusing as to whether it's limits or co-limits. Right. I guess what. Right. So right. I mean, this is right. Hom functors have some sort of limit preserving, automatic limit preserving property or something like that. But in this case, it's going from, it's a contravariant Hom functor. So what is it doing? It's taking co-limits in C1. No, yeah, in co-limits in T1 to limits in set. And we want to extend that property. So we want to make it, take co-limits. The extension should take co-limits, should contravariantly take co-limits in T2 to limits in set. And so, a continuous extension like that is this alternative definition of what a belief is.
So it sends limits, sorry, in T2?
It sends co-limits in T2 into limits in the category of sets. And it can do that because it's contravariant, right? It makes sense for a contravariant functor to take co-limits to limits. That's actually a preservation property. And you can prove, it should be obvious. I'm not sure I can see it right now, but it's supposed to be obvious when you can see what's going on. It's supposed to be obvious. When you're immersed in this, so that it becomes obvious, then it's supposed to be obvious that that's equivalent to lifting along the right adjoint. So continuously extending along the left adjoints is supposed to be, by the adjoint functor theorems, automatically equivalent to lifting along the right adjoint.
Yeah, that sounds believable. Yeah.
So in some way, so one of the slogans that we can use to describe the belief method is we can say that the belief method consists in exploitation of the right adjoints of theory interpretations. So because the doctrines are belief doctrines, that means they include that means the syntax of the theories includes co-limits, and that means, and there's enough, it includes the co-limits are beautiful enough that preserving these co-limits is supposed to be equivalent to having a left adjoint. So, the whole idea was to get into a situation where the theory interpretations are guaranteed to have right adjoints. And once you're in that situation, you're in position to exploit the belief method, because the belief method is really just exploiting the existence of right adjoints to theory interpretations. So maybe I could try to state this in the form of like some fundamental trivial theorem of the belief method. So what do I want to do? I want to say something like, if you have, how do I say this? It's something like, I mean, it's the theorem is telling us, it's instructing us in a very concrete way how to construct the generic model of a theory in certain circumstances. So, right, tautologically, the generic model of the theory T2 is just the objects in T2. But we're tautologically saying that you can think of the objects in T2 as being objects in T1 equipped with a J belief. And that is how it works. So
that's the theorem. So that T2 is equivalent to T1 objects, the category of T1 objects equipped with a J belief. I don't see why that's true. Maybe that you already sort of said that in some other language.
Well, when I get it's because of the equivalence between the two alternate definitions of what a belief is. What the equivalence between the two alternative definitions of what a J belief on a T1 object C1 is. Am I saying this correctly?
I mean, the J belief is giving you this lift object. The J belief on C1 is giving you this object C2 of T2. And so now it sounds like you're saying that that's all, that somehow that's supposed to be, that's supposed to make the category of T1 objects equipped with a J belief to just be equivalent to T2. That is like, that's all there is this object in T2.
Yeah, I mean, well, think of it this way. Suppose for the moment that we had an object C2 of T2, okay? Mm-hmm. Then from that object C2 of T2, we could just apply the right adjoint. Mm-hmm. And that will give us this object C1. Mm-hmm. And that object C1 will automatically be equipped with a belief. By the equivalence of the two definitions, that object C1 will be equipped with this belief that comes from mm-hmm. from it being a strong lift of C2. That will be equivalent to it having a J belief on it. So, yep. So do you see what we're saying? We're saying that.
I mean, that bit didn't depend on any of the conditions or anything here. I mean, that little portion of the result. I mean, you could just say, like, whenever you have a map between sets or categories, an object in one gives you an object in the other. So, but you're trying to say that, like, more than, I mean, that's the easy part. So then there's like the uphill part.
Well, but see, the idea of having a continuous extension, continuous meaning limit preserving extension of the Hom functor for C1. That is a very explicit condition in particular cases. And it gives you a very concrete description of what the T2 objects are. Like, let me show you an example here, okay? Let me see if I can give an example. So, like, let's see.
Yeah, I mean, you have to give me an example to help me understand what this has to do with belief. You haven't really said anything about that to my ears.
All right.
As well as for me to understand.
All right. So let's say, so first of all, we did say that you can relativize this. So I'm going to relativize it in a way that makes it even simpler. So we're going, instead of working over the category of sets, we're going to work over the category of truth values. Okay. So so we're going to, instead of dealing with, locally presentable ordinary categories, we're dealing with locally presentable categories that are enriched over the category of truth values. And so a category that's enriched over truth values, that's basically a poset. And I think the locally presentable ones are basically the co-complete ones. So we're basically dealing with co-complete posets here. So we're looking for some sort of, so again, we're relativizing. So we're going to have a monad on the category of co-complete posets, okay? And, co-complete posets, what are those sometimes called? I don't know, they're sometimes called co-complete semi-lattices or something like that.
The NLAD, they've tried to impose the terminology soup lattice for those.
Okay. But they are co-complete.
Yeah,
right?
I mean, for some reason or other, they've decided. Yeah, I guess soup means like you get arbitrary soups.
Yeah, it could be. So, okay, we'll call those soup lattices. So we're going to have a monad on the category of soup lattices. I mean, I guess it's really supposed to be a monad on the bicategory of soup lattices, but I doubt that makes much difference. But so let's have symmetric monoidal soup lattices. And let's see, I get that might be the same thing as what people call commutative quantiles, now that you mention it.
Yep, I think that's right.
So these are commutative quantiles. So let's give some sort of presentation of a commutative quantile, okay? And then let's use the belief method to construct the generic model of that commutative quantile. In order basically to construct that commutative quantile, to see very explicitly what all its elements are. So that's what we're trying to do here. So so again, note it, right? This is poverty stricken now. This is decategorified. So it's going to seem, right? We're doing that to make it easier to understand. So it's going to be very easy to understand, but of course, it's going to be less impressive, of course. So you have to remember that after we do this poverty-stricken example, we're supposed to go back later and do much richer examples.
I've studied a lot more about posets since we last talked. And so there's somebody I know who likes to study enriching over the Booleans, and I argue that should be called impoverishing. Yeah.
That's
they
good.
had some other name for it, like I can't remember. Depleted? No, I don't know, something like that. Anyway, yeah.
Those sound reasonable. So
you can talk about like impoverished category theory.
Yes, yeah, I like that. So let me just try to make up any old silly example of a presentation of a commutative quantile, and then we'll try to construct the generic model. So we need some generators and relators or something like that. So I don't know, let's try 2 generators, okay? Do you have
Okay.
preference? Do you have preference for the names of the generators?
No, no,
X and Y.
that sounds great to me. Yeah.
Okay. Well, so first of all, let's just leave it at that. Let's not even put any relations. Okay, so just two generators, X and Y.
Okay.
And for this part of it, this is supposed to be the sort of initial setup. So we're not particularly going to try to use the belief method here. We're just going to try to, just figure out by just thinking about it what this free commutative quantile is. So I guess I know what it is. Do you have a description of it? Do you want me to tell you my description of it, or do you want to think about it? I mean, it's right. It's kind of like an impoverished version of polynomials. I mean, polynomials in X and Y. Where the coefficients of the polynomials are only allowed to be 0 and 1 or something like that. 0 or 1.
So is this supposed to be like Boolean functions of two variables? Like truth tables in two variables?
It certainly has a family resemblance to that, but
but it's just but it's not Boolean logic. It's just,
yeah. I mean, because we didn't
quantile
make
logic.
this tensor product into a Cartesian tensor product yet. It's just a
Right. Yeah.
symmetric tensor product. So
Right. Yeah. Okay. So you basically start anding and oring these two propositions, and with and
yeah, right. You can think
ors.
yeah, you can think of it as a kind of anding. It's a kind of symmetric anding. It's just not a Cartesian anding.
Right. Yeah.
But
yeah. What is it? It's still idempotent though. So I mean, it doesn't get to be huge, right?
Doesn't get to be huge, right? Well, it depends what you mean by huge. I mean, should I tell you my answer?
Okay, yeah.
Well, let's see, right? First, we could just take the, right. I think one of the ways this works is you could first take the, you could take the free symmetric monoidal category on this X and Y. So that's just, or maybe free symmetric monoidal poset, right? The free symmetric monoidal poset on X and Y. So that's just something like, I mean, what is it? I mean, it's like
the free symmetric monoidal category would be like two colored, the groupoid of two colored finite sets. But then if you make it a poset, what does that?
Yeah, I think that's right. I think that's right. And then when you make it a poset, it just means that basically, you might as well just remember the cardinality of the number of times that X appears, and the number of times that the color X appears versus the number of times that the color Y appears, or something. So I think it really is just pairs of natural numbers, I think.
Yeah, I'd said that the and was still idempotent, but it's not idempotent. So calling it and is sort of stupid.
Okay, somehow I slipped and I thought you were talking about the or something like that, which is idempotent. Right.
Yeah,
But
okay, yeah.
Right. I did say that it's not Cartesian. I think that Cartesianness is the idempotence or something like that. So it's not Cartesian, it's not idempotent, something like that.
Yeah.
So yeah, so I'm picturing this as a positive quadrant in a two-dimensional lattice.
Mm-hmm.
So like I have coordinates like 3, 5 or something like that. But you can think of it as 3, 5. That's x tensor x tensor x tensor y tensor y tensor y tensor y tensor. Well, did I do the right number of times? So yeah, so that's the way it works. And then, so once, so that was the, that was the free symmetric monoidal post set.
Now it's starting to sound like Rodner Basie somehow.
That's right. I think that's right. Not
yet, but almost. Put in a relation.
That's right. That's right. That's right. That's right. Yes, you can't deny that you know something about Rodner Basie, at least as much as I do.
Okay.
So we haven't put in the the soups yet, but when you put in the soups, you're just getting arbitrary subsets of this quadrant in this lattice.
Yep.
And so that is the universe of believers before we even impose any beliefs. Well, I mean, we could say, right. I mean, it's really important that you don't just believe in facts here. I mean, that's just, among the initiates. Whereas, what is it after the initiates? It's like there's like a hierarchy of
I thought the initiates were more, okay, yeah, okay. More initiated than initiates, yeah.
Yeah, the adepts and the higher adepts, the 33rd degree or something like that. So we're really going to have a hierarchy of different levels of, of belief or something like that. So we're not just, because we're so impoverished now, we're mainly going to be seeing this old-fashioned belief in facts. So,
anybody can believe in facts.
Well, I mean, as opposed to believing in things, right? When you get really advanced, the adepts don't just believe in Boolean things; they believe in the existence of an object and things like that.
Okay, yeah. I thought you meant as opposed to believing in falsehoods, which is what the relations would do in this case.
Right.
Yeah.
No, but we're all right. We're all going to believe in falsehoods. So we're all going to believe in delusions, imaginary things. But right. This is the part that Louvier would really hate, but I don't care. So, right. There's actually a whole long discussion about that, but I'm not going to go into that. So,
anytime I ever said anything about Louvier when he still paid any attention to me, I like regretted it because he like clamped down on me if you ever heard about it. So yeah.
Yes. So
but so far this hasn't, okay, I mean, but so far I didn't need to know the belief method to generate this free structure. I mean, maybe this is some
that's right.
Degenerate case. Yeah, okay.
That's right. So far we haven't done anything that really feels like belief yet. I mean, we can call these the believers though, but the point is these are really the skeptics. These are the, well, I don't know. They're right. We haven't imposed any belief in statements yet, but we're about to impose some beliefs in statements here or something like that.
Okay.
So I just have to think of something for them to believe in. So I don't know what's a good thing for them to believe in. We could try to, don't tell me. How about, don't tell me. I used to have good examples, but I haven't thought about them in such a long time that I don't have any on the tip of my tongue. So I have to make up some silly ones. Might have to change my mind about them if they become too obnoxious or something like that. Let's just try something like, let's impose the axiom X tensor Y. Well, let's see. Okay, so right, okay, so humming out of a soup, a soup is a colimit, so humming out of a colimit, that's kind of boring. So we don't want to do that. We want to do something slightly non-boring. So we'll hum into a soup. Yeah, so let's just try something like that. Let's just try say something like, let's believe in a morphism from X to Y tensor Y. Let's say a morphism from X into Y tensor Y soup, I don't know, 1.
Okay.
Let's try that. Morphism from, what did I say? From a morphism from X into Y tensor Y soup or plus 1, where one is, the tensor unit. Okay, now I made it sound like we're believing in a morphism, but we could make it a little bit clearer that we're really just believing in a statement here. So what am I trying to say? That
I wrote down less than or equal to for my morphism, which looks more statement-ish.
Yes, but yes.
Or you want to say implies?
Well, it could very well be that you're doing the right thing. But I mean, so, well, first of all, I get horribly confused because, right? This is why I get horribly confused because, graphically it looks backwards, right? The less than equal sign is pointing backwards to the arrowhead.
Yeah.
So I get enormously confused by that. But I'll try to pretend that I'm not confused about that. So you were suggesting the idea of, right, so supposedly if A is less than B, or A is less than or equal to B, whatever you call it, something like that. So what am I trying to say? That you can express that as A has, right? You can express it like A soup B.
Oh, you want to express it as an equation, huh?
Maybe that's what I want to do. I'm not even sure what I want to do, but I mean, there's right. A soup B equals B or something like that.
Yeah.
So, or another way to say it is, right, that there's right, B is always automatically included into A soup B. Right, it's like the functoriality of 0 soup B is included into A soup B or something like that. So I could say that I'm taking that morphism from B into A soup B and I'm inverting it. So in all things that I might want to say, I could express as saying that I'm inverting some morphism. But okay, so let's try to think about what are the objects that believe this. Okay, and again, it's supposed to be the objects that believe what? That believe that X well, the way you expressed it was that X is less than or equal to Y tensor Y plus the tensor unit. So in principle, we're really just supposed to apply the definition now and figure out what these believers are. So remember, right, the initial candidates for the believers are just these subsets of this lattice quadrant. And so what are they going to be? Let's see. I mean, we're getting really close to good quitting time. And maybe we should sort of try to make this a homework or something like that. Well, maybe we should just try to get as far as we can on this. And then when we can't, finish it, then it becomes a homework problem and a carryover to the next discussion, okay?
Yeah, that's fine. So
Yeah.
So what style of answer are you trying to?
Well, I'm just looking for a really explicit answer.
No, but this is you're the one who made this up. So
That's right.
so you should like have a clue as to like what kind of answer. So I mean,
Well, okay. I
mean, one way to think of it is like we're taking all these subsets that you talked about, and then we're like saying, oh, by the way, a whole bunch of them are equal to each other now.
Right. That's right. But then we're going to try to pick best representatives for them. These,
So
like
yeah,
confluent things or whatever.
So you're going to try to pick like the least representatives. There's sort of a least.
Actually, okay, right. That's very helpful. What it actually turns out to be, it turns out to be the most inefficient possible representative. It turns out to be. Which sounds unpleasant, but it's actually, it's useful because it it is canonical, and at least gives us something canonical. So okay, but the thing that I was sort of thinking that I wasn't really ready to use this graphics today, but now you're forcing me, I think, to use the graphics here. So you can see something on the screen, is that right? If I start drawing a grid here?
Yep. Yeah, I can.
Why didn't that work?
Well, I saw a blob up here.
Oh, okay, but I need to fix that a little bit better. Where's my erasing thing? That's the erasing thing?
That's your undoing thing, yeah.
Okay.
That's good.
Okay. So this is a really bad picture. Let's see, maybe I should just, instead of drawing the dots, maybe I should just draw the grid or something. The intersection points would be but okay, right. So we've got an x-axis and a y-axis. So over here is the tensor unit.
Mm-hmm.
And et cetera, et cetera, et cetera. Yeah, so in some sense, we're looking for the most inefficient representative of one of these subset classes where, the class is determined by equivalence with respect to this, believing this axiom. So, in other words, you see what I'm saying? If you've got a subset, to fix it, you include as many points as you can without having it change its equivalence class in this model. So, but it's
so like,
yeah.
So I mean, we can do this, the sort of starting point one where which is coming from this relation. So we could like say, we're going to throw in, let's see. We just know that, okay, we know that, yeah, so we write it as an equation the way you've done. And then you're saying like y squared plus 1 is the same as x plus y squared plus 1. So like maybe we could start with y squared plus 1 and then just like throwing in all the other things that are equal to it. How do you draw x? Okay.
It's something like that. So in particular, you might remember that I deliberately chose this axiom so that it would be slightly non-trivial.
Yeah.
That involved homming into a soup rather than homming out of a soup. So the way I recall how this works is that means that when we figure out what the believers are, there will be sort of like these cascading effect where you'll start with some points, and that will be the whole subset. But then the axiom will trigger this cascade and will cause more points to join and more points to join until it stabilizes.
Mm-hmm.
And the distinctive thing about the non-trivialness in this case is that the cascading involves not just a single element in the set triggering another element in the set, but some pair of elements in the subset can trigger something. So it's something like this. It's something like, yeah, I'm still capable of getting this backwards, but it's something like we should look for a pair of elements. Let's see. It should be something like what? Right. I really think it's we're going to sort of pretend to finish today, and then that gives me, enough time over the.
Right. You can pretend we just ran out of time. Don't worry.
Right. So, well, no, but I'm actually going to try for another couple of minutes before I completely give up. But then we won't find out the true answer until the beginning of next time.
Okay.
So I want to say it's something like. What am I trying to say? Well, so let me see if I can get a color here. Red. Okay, so I don't know. Let me start with those. Let me start with that subset right there. So that's an object in the original universe. But we want to see if that triggers anything else. We want to see is that a believer for this thing, for this axiom, or does it need to be, supplemented by, are those elements going to trigger anything? So what am I trying to say? It's like, is there some point in this grid such that when you take X off and put Y, when you take X off, you should get something that's in the set. And when you take X off and increment the Y coordinate by 2, that you would get something in there. So I don't think there is anything like that in here. It'd be like saying something like, I think what this is saying is that if you had like, let me try it. If you had like this element and this element in the set, then I think it would trigger, because this is the one that's like, right? These two elements, one has the Y coordinate twice as many as the other one. Yeah. So it should be something like the X coordinates. It might be that it's triggering this one or something like that. So the closure, right? So I'm saying the closure operator. I'm not sure I did it right. That's what we're going to have to clarify next time, because I haven't done this in a long time. But it's going to be something like, you would take the subsets that are closed in this way, that whenever you have two elements like this that are in there, you would have to include this one as well.
Yeah, and sometimes I think you want the one. Yeah, I think you want the one to the right instead of to the left, because in your original relation you had like y squared plus 1. Yeah, I'm sure you're right. As x, so that had like an extra x. So you want like an. I mean,
extra. You're very likely right, except that I don't trust myself, so I don't trust you either.
Okay. But I get the idea.
Yeah. So right. I think you do get the idea, but we're going to.
But I don't quite see like
why this is so great.
No, just like
how we're going to categorify it. What don't you get?
Oh, just even like.
Yeah. How are these going to form a symmetric monoidal? How are they just going to form a commutative quantile? Say something. Yeah.
I don't know. I guess maybe now I am getting it. So I guess I wasn't getting how you like what it's like to keep throwing in more and more of these guys.
Right.
Like what tends to happen.
Yeah, it will stabilize. It might stabilize with the whole thing being the closure. Mm-hmm. But yeah. So this is what we're going to try to do next time. We're going to try to finish either this example or finish some very similar example, so that we can actually see the belief method working in a very trivial example. But then we're going to try to do much fancier examples that are actually very useful in algebraic geometry, et cetera, et cetera, et cetera. So that's about where we are at the moment. I mean, we're just about to quit. Why don't you have people already coming into the room right now? They're not, this isn't the right time of year. What?
Oh, that seminar is done.
It's done, okay.
permanently, Yeah.
Okay. So, yeah, so I'm just, I think I'm done here. I mean, I'm done here because we're giving up. I'm going to try to do it the right way next time. But that's where we are. So is that a reasonable place to quit for now?
Yeah, that's fine. Yep, that's good.
Okay. So.
Okay, so to get it. Okay, doke.
Okay. I'm going to try to make this much better. This was just the first attempt, but we'll see how it goes. Okay. So thanks a lot.
Yep, it was fun.
Okay, bye.
Yep. Bye.